Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, here we go. We're going to be exploring atmospheric moisture and precipitation today in the first lecture of section 2 in GC 100. So, a little overview of what we'll cover. We'll be kind of just basically introducing water and its properties and then talking a little bit about the hydrologic cycle. We'll come back to that later this semester, and then we'll move into kind of some physical properties of water within our atmosphere, and then kind of tie them to more geographic interconnections with physical processes. So here we go. Some properties of water. Water is H2O, is a chemical compound containing two hydrogens and one oxygen. These share electrons, and that forms this covalent bond. And so because there's H positive and O negative charges, positive and negative charges, these positive and negative polar charges also attract to another, forming the cohesive properties of water, why there's liquid water in ponds and lakes, etc., as well as in our atmosphere. So water exists in three states, in solid, liquid, and gas, and we've previously talked about latent heat energy exchanges and just here kind of reintroducing that and appreciating that there's a tremendous amount of energy that's stored and transferred within our atmosphere due to these changes in state. And so water can exist in as gas, as vapor, or clouds, fog, and precipitation. So we'll talk more about that here in this lecture. So now let's just kind of an overview of the hydrosphere and the hydrologic cycle. As I said, we'll kind of come back to this, or we will come back to this later this semester. But where does water exist? Well, most of the water on Earth is in our oceans. In fact, there's 97.2% of water on Earth is in our oceans, and really only 2.8% of total water on Earth is fresh water, not salty. So that is pretty remarkable, really, when you think about it, because we as humans need fresh water, so there's not that much of it. And then of this 2.8%, the majority of that is locked up in ice caps and glaciers, and most of those are in locations around the world, like Antarctica, for example, where there's basically no humans living, and it's really not that usable, so to speak, in terms of human and society. Then a smaller percentage containing here in groundwater, which we do use, and we'll come back and focus on groundwater later this semester. But then this little tiny sliver being surface water, which if you really appreciate it, since we live, or Marquette, Michigan, and Northern Michigan University are on the shores of Lake Superior, the largest lake in the world, often it's kind of easy to forget that the water is highly limited, at least surface water around the world. There's hardly any surface fresh water on the Earl around the world, at least when compared to all of the water. And so of this, then even a small portion is actually a freshwater lake, where a lot of it is, in fact, in inland salty lakes like the Great Salt Lake and many other salty lakes around the world. And so there's just this tiny little bit of water that then is in our atmosphere. In fact, there's 0.001% as a percent of total water on Earth is in our atmosphere. So that's this like incredibly small amount, especially when compared to the world's oceans. However, it is incredibly powerful and profound. It stores and transfers this incredible amount of energy around the world. And so in terms of its role in our climate and maintaining climatological conditions, it is quite profound. Okay, a little bit more on the hydrologic cycle. Here, the global flow of water to and from oceans. And so, kind of thinking about the balance on a global scale. Again, there's tons of water in the ocean. There's an incredible amount of water that's evaporated from the ocean, and then it condenses, clouds form, and it rains, and it falls back down on Earth, and it flows into all of these different reservoirs, which we'll come back to and kind of think more critically about Earth's hydrosphere later this semester. Some of the major components being rain as precipitation or snow, groundwater flow, and then all of our surface flowing waters. So now we're going to kind of change gears and we're really going to focus on physical properties of water here, especially with respect to weather and meteorology. And so what is this term humidity? Humidity is the amount of water vapor present in the air. And so this is dependent on air temperature. And we'll really kind of focus our attention on this more and more. And you're going to hear me say this next phrase many times because we can understand more complex interactions and processes by coming back to this really kind of direct and simple understanding of how humidity and temperature relate, being warm air can hold more moisture than cold air. And so then vice versa, cold air holds less moisture than warm air. And so I would practice that and kind of get that into a routine of just that basic understanding of this relationship. Again, as we move on, we'll be able to implement and practice this concept in real life and think about why and how and where this matters. So on a grand scale or a global scale, thinking about northern high latitude, cold climates, often because cold air holds less moisture than warm air, there's tremendously less or considerably less moisture in these cold northern climates when compared to more equatorial or warm and wet regions, which have considerably and exponentially more moisture in the atmosphere when compared to cold, dry air or climate locations. So kind of as a comparison then here, so air at room temperature, so about 68 degrees Fahrenheit can contain 3 times as much water at that when compared to freezing. And so we'll see this curve later in a few slides, but then just understand that this relationship is exponential. As it gets warm, that warm air can hold exponentially more water in the atmosphere than cold air. Okay, so now we're going to just simply add this word specific. And so the term specific humidity relates to the fact that we can quantify it. And it's more or less the same thing, but here by adding the term specific, it is a quantity as mass per unit mass, sometimes also expressed in mass per unit volume. And so it is a quantity of water that can be measured and that is contained within a parcel of air. So mass per unit mass. So what is the mass of water per unit mass of air? Because air weighs something, it has mass. And again, we could also think about it more volumetrically, how much water in mass per unit volume, like 1 cubic meter. So to kind of reiterate the point from the last slide, just comparing warm, wet equatorial regions that have lots of insulation and that hot water and then lots of evaporation, there's an incredible amount of moisture as here, specific humidity in the equatorial region. So like multiple times magnitude here, even increase an order of magnitude when compared to these cold northern or southern latitude locations that have, again, comparatively less dry. So again, I'm going to come back to it. Cold air can hold less moisture than warm air, and vice versa. Warm air can hold more moisture than cold air. There's a ceiling, there's a limit. So in the room around you or around me right now, there's this relative amount of humidity, which is the next term. If we reach absolute humidity, which is also known as saturation humidity, this is the maximum. You've reached the maximum amount of moisture that that air parcel at that place in time can hold. And so there's the ceiling. And if it reaches that, if you're almost full, it's still in gas phase. But the second you reach that, what do you think happens at that point? Well, dew starts forming. You might even see clouds. It's condensation directly and most simply. And so there's this like limit at any parcel. And so we're going to explore this more. And so likely in the rooms around you and in the room right here that I'm in, we have not reached this absolute humidity. And you would know if you've reached it because literally there'd be dew on the surface of your desk or in front of you. There'd be dew on the ceiling. You might even have like little clouds in the room you're in. So this brings us to this term relative humidity. So to go back, we can quantify, we can know like the mass of moisture that's in the air around us per unit mass of air or per unit volume. There's this maximum or absolute humidity level that any air parcel, and once it reaches that, it condenses. And so typically in many cases, we have this relative humidity, which is the percentage. So if we're half full, then we're halfway to reaching that absolute. If you're three quarters, you're closer. So 75%, 90%. And then as you reach 99 to 100%, you've reached absolute humidity. So it's just really the relative, the ratio between specific, how much, and that absolute or the maximum. So I like this figure because it's relatively simple, but it also, we can kind of like think about this and even visualize this relationship between specific humidity and saturation humidity. So the absolute humidity. So to go back to the simplest phrase, cold air can hold less moisture than warm air. And I like to think about these like blue squares as literally just like a glass of water. Just like imagine you have this exact known amount of moisture, because that's what that is. We know exactly how much moisture is in the air. And so in this location at 4 a.m., it was 41 degrees Fahrenheit. So a little chilly, right? And then in this location, we experienced this pretty dramatic increase in temperature over the course of the day, which is pretty normal even here in the Midwest. And so it's cold, you're at 100%, you're at that maximum level. And so the amount that's in the air is equal to the saturation or absolute humidity. And then in that case, like literally, if you were standing outside at that place in time, there'd be dew on the grass, there might even be low fog in the atmosphere, which is really just a cloud near Earth's surface. However, it starts warming up, and warm air can hold more moisture than cold air. And so now we have the same exact specific humidity. That like glass of water has not changed, but your air parcel can hold twice as much water. And so in that case, we have a relative humidity, RH, of 50%. And so the quantity hasn't changed, but the absolute value has now doubled. And so the relative humidity is 50%. We continue on our day and we reach this mid-afternoon point, probably about the warmest point of the day, and it's now 90 degrees Fahrenheit, pretty darn hot. We haven't changed that specific humidity. That glass now is the same volume or the same mass. However, this very, very much warmer air parcel in the middle of the day can hold substantially more, one, two, three, four times more, right? And so now we've like decreased our relative humidity. We went from 100 at saturation, it doubled. Our absolute value doubled here, which means our relative humidity is at 50%, and then it went way up exponentially higher, and now our relative humidity is plummeting. And so that kind of gets back to like, I like to practice this figure kind of forwards and backwards. And so maybe some simple take homes to kind of understand or think about. As air temperature rises, if you have not added or removed any moisture, meaning that cup of water is exactly the same, as air temperature increases, relative humidity decreases because warm air can hold more moisture. Oops, didn't mean to do that, than cold air. And then the reverse is true. If we kept going, it would get cold and cold and cold. Or if we just kind of go backwards in time here, if our air parcel, we haven't added or removed that quantity, that cup of water, we can go down and it gets colder, and our relative humidity is going to increase as our temperature decreases. So perhaps if you watch the weather or forecast, you've heard of this term dew point or dew point temperature. And so the term dew point is literally the point at which the air parcel is saturated. And then when we combine them, the dew point temperature is that temperature that the air parcel would need to change to reach saturation. And so it's a mass of air is at temperature at which saturation occurs. So again, to go back to this last slide, if this is how much moisture was in the air and this was the temperature at 90 degrees Fahrenheit, and nothing else changes, you would have to cool down all the way here to 41 degrees to reach saturation. So that at that point in this example, kind of going backwards, or if this graph was like flipped around and we went forward in time and it went to 4 a.m. the next day, it would cool down and cool down and cool down until it reached the dew point temperature. There's this very known like physical chemical relationship between temperature and saturation humidity or absolute humidity. We can literally plot it on this exact exponential curve. And so we can determine what the dew point temperature is at any point in time simply based on temperature. And again, the more water vapor in the air, then the higher the dew point temperature, meaning warm air can hold more moisture than cold air. So the warmer it gets here, the more moisture, meaning the higher that absolute humidity value. In order to reach saturation, like on Earth at any point in time, it is possible, but not as common for like the temperature to stay the same, but more moisture to be added. It's almost like a fog machine or something. You're just like pumping moisture in. This could happen on, local or smaller scales with, especially with like ocean air masses, like funneling a lot of moisture in that might actually be at the same temperature as the land air mass, but now you're adding all this moisture in. And so you can reach saturation by adding moisture into your air parcel. However, more commonly, and really like even on a diurnal, like day to night cycle, and more, you have these like temperature changes, right? So on any given day, you could be experiencing like 10, 20, 30, 40 degrees Fahrenheit or more, or like here 10 to 20 degrees Celsius. And so simply if it was this 25 degrees Celsius in the middle of the day, you'd have to cool down and cool down and cool down to here about 5 degrees, and that is your dew point temperature. It's the temperature your air parcel would need to cool down to, and once it reaches and touches, like literally intersects that line, that is your dew point temperature. Okay, so now we're gonna connect and like apply these physical and physiochemical understanding of meteorology and of our atmospheric moisture content to more kind of a geographical context. And so let's begin with adiabatic processes. So adiabatic processes are where temperature changes resulting from the expansion and compression of air due to pressure fluctuations. What does this mean? And so what I like to like really just appreciate and understand is that air weighs something. It has mass. And in fact, we're in the troposphere. There's mass. There's lots of molecules all around us, and they all have mass, and they're all weighing down on us, like literally. And we, as humans and all organisms, have just kind of been like become used to that much pressure, literally, because it's all weighing down on us. As you go up in the atmosphere, especially like thousands and even tens of thousands of feet, literally there's less mass, less mass, less mass. It keeps getting less and less and less. And as a result, if you track an air parcel down near Earth where we are, there's all this mass pushing down on it. But as that air parcel goes up, it literally is allowed to expand because there's less pressure and less pressure and less pressure. And just like this graphic shows here, it's as it's rising, there's less pressure, and the air parcel is expanding due to the decreasing pressure. And so air cools as it rises and expands. As it expands, it literally cools. And so we know that hot air rises, but as hot air rises, it doesn't keep getting hotter or stay the same temperature. It actually gets a little bit cooler and cooler and cooler as that air parcel is expanding until it equilibrates with its surroundings. And so the exact opposite occurs when air parcels descend for the same reason. Now you have more pressure, more pressure, more pressure, and that air parcel is literally contracting and compressing, causing the molecules within that air parcel to literally move faster because temperature is a measurement of kinetic energy. But then more simply, anytime air parcels descend, they're going to warm up due to compression. To kind of reapply some of a past term, which was the adiabatic lapse rate or this environmental lapse rate. Now we can further understand and separate them into the dry adiabatic lapse rate, meaning the temperature decrease with increasing altitude, or the reverse would be the temperature increase with decreasing altitude. That would occur if an air parcel is not saturated, meaning like you're not in a cloud. And so if you're not at 100% saturation or that absolute humidity, as that air parcel will rise, it will cool at 10 degrees Celsius per 1,000 meters. And so you could convert that to Fahrenheit per feet if you'd like, but just know that that rate's the same, just a unit conversion. And so there's no condensation in this path. And so the dry adiabatic lapse rate is steeper or larger here, the rate itself, when that air parcel is dry. However, then as we learn, so air parcels expand as they rise and they get cooler and cooler and cooler. And what do we know about cold air? Cold air can hold less moisture than warm air. And then I don't like to usually do this, but I want to go back to this one kind of property. And so as that air parcel rises, the temperature is cooling and cooling. It's cooling, just like here my cursor. So now your air parcel is cooling, it's cooling and cooling. And at some point it cools to the dew point temperature, and voila, clouds form. And so when that happens, now the air parcel continues to rise, but it's rising under saturated conditions. And we call this the wet adiabatic lapse rate, which still cools as it rises, but it's cooling at a slower rate. And so that rate is not as steep. It cools much slower as you go up. And the more, or importantly, then the reason it happens is due to latent heat energy. And that's the extent that we need to appreciate why in GC 100. All right, so now let's just think about precipitation and clouds, because clouds are cool. And so here a little bit about cloud formations. Clouds are classified based upon form and by altitude. And so for GC 100 here, we're just going to have some basic understanding of cloud form and altitude, just to appreciate that there are subdivisions into these major form and altitude classifications. However, for GC 100, I'm not expecting you to know the differences between cirrocumulus versus altostratus. If you took like a weather and climate course, you would investigate or examine that in greater detail. But I think it would be useful to appreciate these really high altitude cirrus clouds, which are our wispy clouds. And so that's your highest cloud is a cirrus cloud. Your middle altitude or middle elevation clouds are cumulus clouds. And I like to call these Simpsons clouds. If you've ever watched the show Simpsons, pretty much every day have these perfect shaped kind of like cartoon clouds, right? That's a cumulus cloud. So that's your middle elevation cloud. And then when you have these low clouds covering the sky and you can't see them, and the clouds actually literally are low in elevation, meaning they're close to Earth's surface, these are called stratus clouds. And so we'll explore here and then moving forward some of the different clouds, especially cumulonimbus clouds, which are thunderstorm clouds. But as mentioned, I would just be able to compare among these major categories of form and altitude clouds. So what are clouds? They consist of water droplets, ice particles, or a mixture of both. It's where cloud drops condense on small particulates, and these particulates are called literally cloud condensation nuclei. And so the tiny little particles form the nuclei at which and then it condenses. So water condenses on that particle, and literally like most moisture, water, especially rain falling from the sky, there's a particulate right in the middle of that formed that original condensation drop, if you will. This can be a particulate like dust. It also could be salt. So exploring clouds here closer to Earth's surface, when a cloud occurs near Earth's surface, it's called fog. And so fog is a cloud layer at or near Earth's surface. And this can happen for a few reasons, which we'll explore here and in the next slide or two, where air temperature at the ground level falls because cold air can hold less moisture than warm air. You reach saturation or absolute humidity, voila, clouds form. And when that happens near Earth's surface, you have fog forming. And so forming this often, these types of radiation fog often form in low-lying areas and valleys. If you ever driven across the landscape here in Marquette, often if you're driving from here south towards Escanaba and 41, you'll kind of like come in and out of the clouds a lot as you kind of go down into these dips and back up. And that is radiation fog. Other ways that fog forms is through advection, like literally moving air parcels or air masses moving in or out of areas. And so in this case, advection fog forms when warm, moist air moves over a cold surface. You have this like lots of moisture in warm air because warm air can hold more moisture than cold air. I'm going to keep practicing that. And then that warm air comes over the colder water, the temperature drops and cold air holds less. You've reached absolute humidity, the dew point temperature, and voila, clouds form. And they form at the surface here. And often this happens in these kind of land sea contrast regions where you have this warm atmosphere. Air then moving over colder water, and you have this kind of fog forming, over the surface of the water. This can really just happen on the water itself. And so, like, as water moves or as air parcels move above water, especially on a large scale, like oceans, but even also Lake Superior have large currents. And so, where you're in some of these currents, the temperature of the water can be dramatically different than the water temperature outside of the current or upwelling zones, for example. So, as air masses move over water, that differing temperature of the water can also literally create fog. And so that's called sea fog. So precipitation forms within clouds when droplets or ice crystals get large enough, literally in mass, and they fall to Earth. And they fall to Earth in these various forms. And so they form as rain, which is an unfrozen water droplet. They form as snow in the winter, which I really appreciate. And then they form as sleet, which is rain freezing before it hits the ground. So this is the stuff that kind of hurts, right? A little bit. It's like little frozen water pellets. If you see a forecast or hear a forecast for freezing rain, that's when liquid water reaches the ground and freezes at the ground, and that can be incredibly hazardous for driving and transportation. And then last but not least is hail, which is actually kind of cool. It's this water droplet that's froze and then melted and froze, and it goes through this cycle of freezing and thawing multiple times. And the more times it freezes and thaws within the atmosphere, the larger it gets. So now what we're going to do is we're going to break precipitation, kind of like connecting the physical properties with these geographical processes and concepts into four major categories. And so precipitation occurs when air masses rise sufficiently high enough because as air parcels rise, there's less pressure, they're expanding, there's less pressure, they're more expanding, and they're cooling and they're cooling, and they reach that dew point temperature, at which case clouds form. And so precipitation occurs due to this increase of air mass. The reason why air masses rise can be broken into these four major categories. We're going to cover each one of these four major categories, and I'll come back to these two many times. But here, for this lecture topic, we're really just going to focus on convectional and orographic. And I'm actually going to start next with orographic, and then we'll move to convectional. When we start kind of appreciating and understanding what we call frontal and convergent uplift, this is where it becomes more understanding of like weather systems, cold fronts and warm fronts. And so that we're going to dedicate really an entire lecture to understanding both frontal and convergent uplift processes. So next here, we're going to define orographic and convectional processes. So what does orographic mean? Literally, it means there is a big ridge or a mountain in the way, and the air mass is moving over the land, it's moving over the land, and it reaches that ridge and it has to go somewhere and it can't go down into the ground, so it's gonna go up. And so when airflow is interrupted by a mountain range, it rises, it rises, it rises. And even here in Marquette, between here and Ishpeming or Michigami, we're thinking like almost 1,000 feet of elevation change as you go up toward Michigami. But in the mountains, especially through California and Pacific Northwest, you could be thinking of like tens of thousands of feet of ridges and mountains in the way. And so your air parcel is rising, it's cooling because it's expanding, and it reaches that dew point temperature, absolute humidity, at which point clouds form that keeps rising because it has to, because the mountains are in the way. It keeps cooling because as air parcels rise, they're expanding and they're cooling. And so now it's cooling at the wet adiabatic lapse rate after it was initially cooling at the dry adiabatic lapse rate. And so on this windward side of mountain ranges, you have a tremendous amount of precipitation and clouds forming. It's really cloudy, it's moist, and it's humid, and there's lots of rain. That air parcel reaches the top and then it is literally forced back down. And so on the leeward side, the exact opposite happens because as air parcels descend, they're constricting and they're getting smaller and more compressed and they're warming and they're warming and they're warming. And warm air can hold more moisture than cold air. And so as air temperatures increase, relative humidity decreases, and it's getting effectively drier, or there's less moisture, precipitation falling here in that case. So California is a really great example of orographic processes. There's many places we can cover, but here we'll just kind of focus on the California topography. And so there is this distinct coastal range of mountains in California. They're pretty darn big. They're not quite as big as the Sierra Nevadas, but they're big enough that there are most definitely orographic processes. We're on the windward side of these. It's pretty moist and humid. It's even like a temperate rainforest in some places. And then that air parcel rises to the top of that coastal range and it passes over what's called the Great Valley here, which is Central Valley, often it's also called. And that is actually this arid, semi-arid condition because you have that air parcel falling back down. Now it's warming and there's less precipitation. And so you have this semi-arid condition. And then boom, it hits the Sierra Nevadas, which are huge, and it goes way up and back up, and then it cools again. And once again, you have a tremendous amount of clouds, moisture, and precipitation on the windward side, and then it gets to the top and it gets over and it goes into the bigger geographic region known as the Great Basin, complete with the Death Valley, the hottest and driest place in at least continental US. And oop, oh, I went a little too fast. Okay, we'll do that one more time. And so I truly love orographic processes. I think about them all the time, and I really thoroughly enjoy them. Here, both pictures here from out west, this one in the Manti La Sal forest, the La Sal mountain range near Moab, Utah, and this one taken near Silverton Mountain Resort in the backcountry there in the San Juan range of Colorado. But I do some of the same things around here and also enjoy orographic processes right here in Michigan. So moving on anyways, a little bit about convectional uplift. So as promised, we talked about orographic uplift and now here a little bit about convectional uplift. We'll talk about both of these more moving forward. And again, we'll have this whole like kind of dedicated lecture content topic next, focused on frontal and convergent methods of air masses rising and falling. So here, convective uplift. Moist air is warmed at the surface, literally, and often we have radiation, insolation coming. It's warming and it's absorbing at the surface, and you have lots of long wave radiation emitted from both the atmosphere and the surface. That temperature rises, and when air warms up, it rises. So air rises as it warms, and as a result, you have convective uplift. And so now as that air parcel is rising because it's warm, and then As it rises, though, however, remember it's starting to expand and it's getting cooler and cooler and cooler. And you reach dew point, and that point at which you reach dew point temperature, your relative humidity now, right then at 100%, clouds form, and it might even start raining often for many reasons, as this convective cell can even grow further and really high up into the troposphere. It can keep rising at that wet adiabatic lapse rate. And as these cumulus clouds have tremendous, are like fueled by more, there's just more coming and more coming underneath. And so as there's more and more coming from underneath with all that convection, you can like literally extend those cumulus clouds up vertically into the troposphere, and they become what are known as cumulonimbus clouds. And we'll talk more about this specifically in a future lecture topic, but just understand that due to this, when there's a lot of convection, really, which is simply driven by lots of insulation tying to previous lecture topics, the more the heating, the bigger the updraft, literally, the bigger the clouds form, and the more the friction, and these can create these very strong, powerful, intense thunderstorms. So, with that, we'll end on thunderstorms. Dr. VG is signing off.